Hello everybody, welcome back. My name is Brady Erickson, again here with the Technical Service Department. And today is going to be another Inner Circle, and this is going to be part 2 of our acceptance factor training. So hopefully a lot of you watched the part 1. That was kind of the foundations of what we'll be talking about today. You know, the acceptance factor formulas, drawdown calculations, and just some of the more high-level stuff. And as promised, today we're going to dive in deeper with how we can use that for specific applications, how we can compare some of our Amtrol product that we may have the same max acceptance on, and that's a big question out there. We're going to try to explain that as best as we can today, as well as some competitor comparisons, so some popular tanks that we see out there from that standpoint that we get a lot of crossover questions, or can we compete with them? Can we apply our tanks when theirs are specified on the schedule for a bid or something like that? So I'm going to try to answer as many questions as I can today. We're going to dive into that and really try to see if we can get a real good confident foundation built on a lot of those topics. As always, we're going to have a Q&A session at the end. So once I'm done the presentation, we'll take a 5-minute break. We'll collect all those questions you ask, and then we'll be able to answer them live on air. That way we can clarify anything we need to clarify or answer any questions we haven't touched on throughout this. Like I said, so if you want to pay attention, you can send those questions in during the break. We'll still make sure we get to them. So without further ado, I do want to jump in. This is going to be a little bit of a longer one, just like last time. It's just there's a lot we want to cover, and there's a lot I want to tell you today. So I'm going to have Gabe bring the deck right up. And again, just to highlight what we're going to be talking about, we're going to be adjusting our drawdown to fit certain applications. We're going to compare max acceptance of tanks, and then we're going to do a brief competitive analysis at the end. So going into the start, some of these slides might look familiar for those that have been in part 1. They're obviously going to be new if you missed part 1, and they're going to be essential going forward. So I did want to touch on them again very briefly. This is how you can change the acceptance factor of your tank. And what I mean by that is how we can take a tank that normally would hold 11.8 gallons at 40 to 60, and we can increase it to maybe like 17 gallons if we just lower that pre-charge a little bit. We call it supplemental drawdown. Before I even go into this, one thing I want to note with supplemental drawdown, and I know I mentioned it in part 1 as well, I think it was one of the questions we got, is this something that's good for the tank, or does it make the tank work harder? So we dove into a little bit, I thought about it, and the answer is yes. It's not something you want to do all the time if you can avoid it. There's a reason why we recommend 2 pounds below your cut-in. That's for a reason, because that's where the tanks are meant to be operating at. That's their sweet spot, if you will. So when we talk about these situations for supplemental drawdown, you don't want to apply that to every single install. You only want to apply it if it's one of those niche applications or it's something that's specifically required to make sure that we're going to solve the customer's problem. We don't want to do it in every tank because we're going to be swallowing that diaphragm up a little bit more. It's going to be higher in the tank. It's not in its normal operating zone anymore. And this goes for any diaphragm tank. So I just want to make that little disclaimer as we go into this. It is important, but it's not for everybody, or every system, I should say. So we have that tank as a setup right now. You can see the acceptance factor is 0.27 between 40 and 60, and it gives a 44-gallon tank, so it'd be like a WX250, for example. It would give that tank 11.8 gallons of drawdown. On the left-hand side here, we're going to manipulate that a little bit. So what I'm going to do is I'm going to take my drawdown calculation formula. I'm going to use that same 44-gallon tank, but instead of 40 to 60 with 38-pound pre-charge, I'm going to lower that pre-charge all the way down to 30. So I'm taking 8 more PSI out of the tank. But what that's doing is instead of 40-60, it's going to be operating at 30-60. So I'm increasing my differential, which as you can imagine is going to increase our drawdown. But we're going to see by how much. So by running through that formula that we showed in the beginning, we're going to get a new total drawdown of 17.7 gallons. And on that little middle picture there, you're going to see that extra volume that's introduced at the bottom of the tank. And that's what we call that supplemental drawdown. So if the switch is still going to, in this scenario, the switch is still going to click on at 40. That's still your cut-in. But that extra volume is going to be used for what we call peak demands. So if it's a commercial system, or if they, I don't know, maybe filling a tub, I guess that would be an example. But just anything where you just have a high flow for an intermittent period of time. That's where supplemental drawdown is key. You're not using it every day. You don't need to always have that volume utilized. But if you're going to exceed your pump demand and you know your pressure is going to drop below and your pump can't keep up, you can use a tank with supplemental drawdown to make up that difference. And again, we'll give examples, but that's where this is going to lead up to. But as always, we don't want to forget what the max acceptance of the tank is. And then I know that's always the key factor. Oh, the max acceptance. So every vessel, no matter what, it's always going to have a specified max acceptance rating. It's just how far can that bladder or the diaphragm move within the tank. And again, it's decimal, but it's really a percentage. So this 44-gallon tank, and we used ours for example, the most it can flex, or the most that diaphragm can go without stretching to a dangerous point, is 77. So 0.77, which is 77%, which in a 44-gallon tank would yield over 33 gallons. So in both the scenarios, we're well below max acceptance. So again, that's just something to be aware of. Okay, 0.77, I'm 0.4 in that scenario. I'm well below, so don't even need to worry about it. But if you were going to really start going crazy on that tank, if it was a smaller tank that maybe had a smaller max acceptance, 0.40, you might be getting close. So it's, again, be aware of it, but it's not going to come into play for every single tank. You just need to know not to exceed it if you're going to go down this supplemental drawdown route. So moving on here, before we jump into the new stuff, I want to reiterate max acceptance. So I'm going to read that definition again. So it's very, very important. So the most drawdown that any fixed bladder or diaphragm vessel can hold without stretching the bladder or diaphragm. And again, I underline that can. It's not a guarantee. So if your tank has a max acceptance of 25 gallons, the tank's not going to hold 25 gallons. It's only going to hold what the pressure range on your system allows it to based on that's acceptance factor. It's going to be, like I said, 9 times out of 10 a number below that. So it's like how much it can physically hold, but not how much it will hold in practice. You need to talk to them about their system parameters to figure out how much volume that tank's going to hold. We don't dictate the drawdown every time. The system dictates the drawdown. Depends on the pressure range. The acceptance factor becomes more important in the scenarios that I just mentioned when you have a larger pressure or temperature differential. So as you increase that differential, that acceptance factor number is going to get higher. So if you were going to increase your typical differential from standard systems 20, if you're going to go 30, 40, 50, now you're getting into some dangerous territory. We got to start paying attention to max acceptance. We don't want to damage that tank. So it's more prominent in those situations. And then a full acceptance tank is not truly 100% acceptance. We get this a lot with folks that are sizing full acceptance tanks like an L series or one of our other ASME tanks with a full acceptance bladder. If they run their calculation and they get 128 gallon tank requirement, they'll size a tank that's 128 gallons for drawdown. So if I need 128 gallons of drawdown, they'll put a 128 gallon tank in. Those numbers aren't the same. The total tank volume and drawdown volume, as we know, are different. Drawdown is always a percentage of your tank because you have to put air in there. So if for an L series, again, that's probably the most popular one because they'll calculate their expanded water and they'll, I have 300 gallons of expanded water, I'll use a 300 gallon tank. No. You're going to have probably a 500 or 600 gallon tank because only 50% will be used for drawdown depending on your pressures. So it's very important to note. It's a quick misconception. It's usually easily explained. It's like, hey, remember you got to have air in the tank for it to be a hydropneumatic tank. Otherwise, it's just a big tank full of water that's not doing anything for expansion because you have no pressure in there. So it's just one thing to keep in mind that if you see 1.0 or 100% or full acceptance, it's not holding the full vessel's volume in water. And then basically reiterating what I just said is Boyle's law. So that's the reason why I say that stuff is because that is the physics that require that to happen, right? So you have to have air pressure in the tank in order for it to do its job. That air is what's compressing, it's what's pushing the water out. It's very important. In Boyle's law with P1 V1 equals P2 V2, if you're going to increase your air volume, you're also going to increase your drawdown, so they work off each other. So you need to have a larger tank vessel in order to allow it to fill with more water. Obviously, it's all proportional. So it's very important that we follow those rules, we follow Boyle's law, and that way we're explaining our tanks correctly, but also we're applying them correctly. We know we're not going to get a customer in a scenario where they were just misunderstood and they didn't understand why they were getting the tank they were getting. We can guide them to the right place. So now we're going to jump into some of the new stuff. So now we're going to start applying those concepts we learned about in Chapter 1 and just some of the stuff I refreshed there. So supplemental drawdown, how can we utilize that? I said how we can do it, by lowering the precharge, but where does it really come into play? How do I size a tank for supplemental drawdown? Like, how do we even begin? So some scenarios where supplemental drawdown is useful, just giving examples of things that I've sized in the past, is usually larger industrial applications or just some commercial buildings or areas where they have, obviously, like I note here, intermittent high flow demands. Just for a more detailed example, I sized for a college campus. They were just installing a new science lab addition, so they put all this new equipment in. I wasn't familiarized with the equipment itself, but I was told that it had a washdown cycle. And what would happen is it would run out of water. The demand from the main, or excuse me, the supply from the main wasn't able to satisfy the demand. It's a very common thing. We all know if we build, with COVID, we build additions onto houses. We may have added another bathroom and they don't run any flow tests on the system and they realize that, oh, I can't flush a toilet in the new addition if I have the sink on. We just run out of water. Very popular, and then they try to put an RP in and it doesn't work, but we'll handle that another day. So here's an actual solution to that problem, is we can introduce a pressure vessel to have supplemental drawdown. That way it can have the volume ready under pressure to satisfy that demand when needed. So I'm going to give an example here. So what if I have an intermittent demand of 15 gallons per minute, but my city supply is only able to give me 10? So obviously we know there's a gap there. We're missing 5 GPM. So right away we're like, okay, it's not a pressure problem. We're not running out of pressure. We're running out of water. So how can we solve that? So by digging deeper, we're going to have to ask a few questions, because as always, we basically got to become experts on their system as much as we can in a very short amount of time, usually over the phone. So we got to ask some key questions to make sure we're understanding how we can apply our tanks. And there's only 5 questions we need basically to ask, and I have them listed here. So we're going to need their peak demand, which in this case is 15 gallons per minute. We're going to need their available flow rate from whether it could be a well tube, but whether a well system, a city supply, whatever their supply is, in this case it's going to be 10 gallons per minute, and that's obviously where our gap's going to be. And then you're going to have a minimum pressure, and that's what we're going to set our pre-charge to. So a lot of times the minimum pressure comes from whatever the equipment that's running the demand, or whatever it is. So for this example, I chose 40 PSI. So what if that piece of equipment in the science lab, the valves on there or the solenoids, whatever they were needing to use, required a minimum of 40 PSI to actuate appropriately. So usually they'll specify, well, I need at least 40. Okay, cool. So that's going to be our minimum pressure requirement. We're going to make sure we keep your system above 40 PSI. If they don't have a number, talk to them, agree on a number. A lot of times they go, well, how can we do 50? Does 50 make sense? Yeah, 50 makes sense. So sometimes you have to force them into giving you a number. But ultimately, there's always a minimum requirement somewhere in their system that they have to have, and that's what that minimum pressure is going to be. In this case, 40 PSI. And then you're going to have your max pressure, which for a city supply is just going to be your static pressure. If this was on a well or a community well or anything, it would be the high limit, the cutout pressure. Basically what you can see we're doing here is we're building our pressure gap. So we're going to have our minimum required and then our maximum given, and that's how we know how much room we have to work with. And it's going to give us our acceptance factor for those that are following along. So stay tuned. And then we're going to have to ask, how long do you have that demand for? So I have a 15 GPM demand and my system's running dry. Okay, well, how long do you need that 15 GPM for? If it's for 1 minute, okay, you can handle that. If it's for 3 minutes, now we got to work 3 times as large because we got to cover 3 minutes worth of that demand. So it's very important to know. Sometimes it's in the 15 minutes, 20 minutes, which you're going to put some big tanks in, but we can handle it. This scenario, I chose 3 minutes. So once we get all that information, like I said, get those 5 bullet points down, now we have what we need to size the tank. So on this right-hand side here, I'm going to start going through the 3 formulas we have to use to get our total volume. The first is we got to calculate our drawdown. So, okay, we know that there's a gap, and we know we have a time frame for that gap. Now, how much volume do I need to make sure we can bridge it? So what you're going to do is you're going to take your flow rates. So in this case, it's 15 gallons per minute minus the 10 gallons per minute, and you're going to get 5 gallon per minute difference. Multiply that by 3 minutes. 5 times 3 is 15 gallons. So we know our tank needs to hold 15 gallons between 70 and 40 PSI. And why is that 70 and 40 PSI important? Like I hinted at earlier, that's going to give us our acceptance factor. So the acceptance factor between 70 and 40 PSI, or 40 and 70, depending on which way you're looking at it, is 0.35, so 35%. So we know basically here, okay, so if I need 15 gallons and only 35% of any pressure vessel is going to be utilized at that pressure range, now I kind of have something to work with. So our last formula we have there is our drawdown needed divided by the acceptance factor is going to give us our total tank volume. So 15 gallons is what we need. 35% is what any pressure vessel is going to hold. We're going to need a 42.9 gallon tank. So we'll call it 43 gallons. In that case, our 44 gallon tank will work. You could put a 250 on that scenario and it'll work just fine. that's how we size for supplemental. So we kind of almost work backwards. Instead of sizing a tank for a system, we're using that system to size a tank. It's, you know, it's all the same formulas, you're just looking at them from a different angle. But this is, again, crucial a lot of times with those bigger commercial or industrial applications where they have those quick, whether it's sometimes it's like a fire hose, that they have, there's always a weird scenario where they need more water than they're given. So instead of having like a booster pump and a cistern or some larger setup, this is a very viable solution for them. Yes, it sells as a tank, but also it's a smaller form factor. It's already pre-pressurized. It's ready to go. As long as they have good static pressure, I mean, a hydropneumatic tank probably is the best way to go because you don't need all that extra equipment, all the electrical and all that fun stuff. It's probably a much more affordable option 9 times out of 10. So hopefully that made sense, but I want to jump into another scenario here with maybe a little bit of a smaller tank or something more common we see is flush valves. Very, very popular scenario. You have Sloan valves, flushometers, all those different tankless flushing devices out there. A lot of times, unfortunately, you run a really small half-inch pipe to these things and you flush 3 at a time and there's absolutely no water. They don't flush. Very, very common problem, unfortunately, out there as builders, but we have a solution for it. So for this scenario, I'm going to give an example and I'm going to show you how we would size a tank for it. So for this example, we're going to do a small men's bathroom. There's 2 urinals that have flush valves on them. Every flush valve is going to be rated for a gallons per flush. So that's basically their flow rate. So for these examples, usually it's between 1 and 1.5. You get, at least nowadays, you find sometimes there's old ones that are like up in the 2s, but usually you're between 1 and 1.5. I chose 1.5 for my scenario. So I have 2 flush valves doing 1.5 gallons per flush. And then we're going to have to ask the static pressure again. So remember, the higher the static pressure, the better off they are. As always, the more pressure, the more you have to work with. So, for example, if they didn't have a lot of pressure and they didn't have a lot of flow, so say they, hey, I don't have enough flow to flush these toilets, and then you ask them what their static pressure is, and they're like, oh, it's 25. Like, ooh, it's not a lot we could do there because we don't have any room to work with. So they would have to either size up their piping and put a booster in. They'd have to kind of do something to make sure we can get the static pressure up higher first, and then we can apply our tank. This scenario, I'm going to assume one or the other. Either they had good pressure or they already took care of their lack of pressure and got it up to 60, so now we have something to work with. So I'm going to say their static pressure is 60 psi. And then again, you're going to have to find that minimum pressure. So again, from working with these systems, I've figured out that minimum pressure requirement for most flush valves are between 30 and 35, give or take. I usually do 35 just to be safe. That's my choice to size with these, and we've never had any issues, so I kind of stick with it. So 35 psi is my minimum, 60 is my static. So again, that's how we're going to build that acceptance factor out of our vessels. So those 4 pieces of information are very crucial. And then we're going to go through a very similar formula. So now let's find out what do we need for our drawdown. So if I have 2 urinals at 1.5 gallons per flush, just do that math quick, it's 3 gallons. So I need 3 gallons in my tank under pressure, at least 35 psi, to make sure I'm flushing both of those at the same time. So based on my pressure range, I'm going to get my acceptance factor. You run that formula quick and you're going to get 0.33, so 33%. So again, we need a vessel that at 33% of its volume is going to be 3 gallons. So by putting that in formula mode, our drawdown needed of 3 gallons divided by 33%, it's going to give us 9.1 gallons for total tank volume. So for 2 urinals at 1.5 gallons per flush with 60 psi static pressure, I need a 9.1 gallon tank. So in that scenario, again, we have to look at our offerings. It'd probably be a 201. So that's 14 gallon tank. So we could put a 14 gallon tank for those 2 flush valves, and we'll have enough volume in that tank already pressurized, ready to go to discharge when that flush valve activates. So they won't have any loss in their system. They won't overdraw it. They won't dump all their pressure out, and they'll be ready to roll. So I'm going to show an example here. Gabriel made a very good graphic of kind of what this is doing, just to try to help visualize it. So on the left-hand side, you have your flush valve. The right-hand side is you have, in this case, it's just an inline well tank, call it a 102, 103, doesn't matter. But what's happening is when the flush valve activates, you see that the pressure in the tank is going to push all that water volume out, obviously out to the place of low pressure, which is atmosphere at this point. Once that valve opens, that water is going to discharge out, flush the toilet, and get everything taken care of. Once that valve shuts again, you'll notice that the tank fills back up. Like, well, how's that happening? Because there's static pressure in the system, right? That's why static pressure is important, because that's what's going to refill the tank back up. So once that valve closes, system closes back up. Now that system has the chance to repressurize up to its static of 60 psi, which is going to repressurize that tank and fill it back up with its 3 gallons and change of volume. So that way, the next time they flush, you already got the volume ready to go in the tank. But because the system shut off, there's no extra demands. Even if you had really low flow through that main, it doesn't matter, because all that flow is going to do at this point is just slowly fill that tank back up. You're not overdrawing your system demands by any means. So this is the flush valve example, but it would be the same for, it could be a 1000L or a really large ASME tank. It's doing the same thing. When that demand opens up, the tank's going to discharge its volume to satisfy the demand, and then once it's done, the tank's going to fill back up with the static pressure or the well pump or whatever it's using. So it's similar to how normally we size a pressure tank, but you could tell it is different. There's a different way we have to look at it. There's different questions we have to ask, and the pre-charges aren't just going to be 2 pounds below cut-in, because on a city system there is no cut-in. There's a lot different ways to look at it, and we have to make sure we're handling it right. So those formulas that we showed you on those prior 2 examples, those would size almost any system I can think of. Most questions that we've run into, most different sizing scenarios, those are the formulas we've used. We've gotten them a tank, we've gotten their problem handled. But hopefully this illustrates kind of how that tank's going to function in its lifespan. It almost functions like a thermal expansion tank if you really think about it. It's filling when the tank is when the system's closed loop, it's going to fill up with pressurized water, and then when the system opens up, it's going to discharge itself. So obviously we have some experience there as well, so that's why we're able to work these tanks into all those niche applications. So now let's jump into some comparisons. So we're going to start off with a couple Amtrol comparisons just between our 2 products, and then like I promised at the end, we'll compare some competitors as well. So this is going to answer that age-old question of, I have 2 tanks with 2 different volumes, but they have the same max acceptance. We have, just from this is the WellX example. A WellX 201, 202, 202XL, and 203 all have 11.3 max acceptance. They all have the same water dome. So the question is, okay, why am I using a 201 and a 203? How does a 203 hold more water if it's the same max acceptance? Which, again, it's a good question because it's hard to visualize. That's kind of what I'm going to try to handle here. Max acceptance, like we've talked about, is a physical constraint within the tank. It's the most that diaphragm can invert itself without stretching. That doesn't mean that's how much water the tank's going to hold, as we know, as we've talked about multiple times. So I'm going to give a scenario here, and I'm going to show that out. So I have my control system set up. It's my favorite system is my 4060 switch with 38 psi precharge, and I have a 202 and a 203 next to each other. Just imagine these are installed on a system with 2 ball valves. So right now they're both isolated, but they're on the exact same system. So a 4060 switch, as we know, no matter what tank we have, is going to give us 27%. That is the acceptance factor of 4060. That is the switch telling us, basically, at 4060, your tank's going to hold 27%. They say it to us, they say it to Flexon, they say it to Wessels. The switch dictates your acceptance factor. So 27%, that's what we have to work with. And then I also note there that both these tanks have a max acceptance of 11.3. So where's the differentiation come into play? So if we look at it, we got to remember that acceptance factor is a percentage. So if we have 27% of 20 or 27% of 32, what yields more water? Well, the bigger number. So if we have 20 gallons at 27%, that's going to give us approximately 5.4 of drawdown. If we isolated that tank and opened up the 302 on the same exact, not 302, excuse me, 203. So if we isolate the 20 gallon and open up the 32 gallon, we don't change anything about the system. It's on the same system. We just put a different tank on. Now that tank is going to hold 8.6 gallons. The exact same system, different drawdowns because of the total volume of the tank. Not the acceptance volume, the total volume. And it goes back to Boyle's law. That air volume is very important. So the more we build air, I mean, we could build this tank to the moon if we wanted to. Obviously, you couldn't move it. But all that air volume, it could have the same water dome. That diaphragm is going to stretch way more because you have that extra air volume. Obviously, there's a limit to that. That's why our tanks aren't 10 feet tall. But the concept's there. So if we kind of just wire our brains to think, if I don't look at max acceptance right away, I just kind of put a sticky note over it, I don't look at it right away when I'm looking at these tanks, Instead, I look at the pressure range on the system. I look at that switch first. I take the cap off, I look at it, and I say, okay, it's a 40-60 switch. I know that that's going to give me 27% tank volume. You're already all set. You figured it out. You're like, you're there. So now you can take any tank volume, 20 gallons at 27%. Okay, that's 5.4. Well, what if I want to size up? Okay, well, I could put a 203 on here. Now I know I have 8.6 gallons. So now I have more drawdown. I'm not changing footprint, it's still the same max acceptance, but we're not using max acceptance. We're below it on both those scenarios. It's the switch is what tells you how much water the tank's going to hold. It's really what it comes down to. And I know it's not the first intuitive answer you give yourself, but that is why. It doesn't matter what the max acceptance is unless we're doing those supplemental examples in the beginning, then it's important. For standard pressure switches, you'll never exceed max acceptance, else there would have been issues in the field since the 60s, right, when these tanks were invented. Those pressure switches are all on safe grounds. 30-50, 20-40, 47, 50-70, they're all fair game. But that's what's going to tell you what your drawdown is, not your max acceptance. I want to give another example, just to try to look at this from a different angle, because I know not everything's well tanks. Well tanks have switches, so it makes it a little bit easier maybe. So I'm going to complicate it a little bit. All right, what about an expansion tank? I have two tanks here, an SX40V and an SX60V. So it's the same total volume sizing comparison as the well X-Trolls, but now it's going to be on a different system, obviously, right? This is a X-Troll, so it's going to be on a hydronic system. So I'm going to have different variables I have to figure out. I'm going to have to figure out, instead of a switch, now I need a precharge or my fill pressure on the system. So this system, is going to have an example of 15 PSI fill. 15 PSI fill, 30 PSI relief. Again, a very common system. Between those pressures is going to yield me 33% or 0.33% acceptance factor. And again, it's going to be important as we go forward. So, and that's why we ask about pressure ranges too, if you're curious on all those sizing charts, is because that's how we know what our acceptance factor is going to be. On expansion tank systems, or so your hot water heaters, your air boiler systems, you're going to calculate what your expanded water is. That's part of the formula. It spits out your expanded water. It's your total volume of your system times your expansion factor gives you expanded water. So in my example, my expanded water is 5.53 gallons. So that's what my drawdown is going to need to be within the tank, is going to be 5.53 gallons, because that's what the expansion my system is going to create. And again, on these tanks, I have a max acceptance of 11.3. So by looking at it off the bat, you're like, okay, well, I have 5.53 gallons of expansion. My tank's going to hold 11.3. I'm good. That is correct. But then the question comes to, well, okay, so I know I'm good, but I have 3 tanks that all have the same max acceptance, so which one do I choose? Or why would I get a larger one than a smaller one if they all have the same max acceptance? So the same question still comes into play. We're just going to answer it a little bit of a different way. So again, acceptance factor, very important. So the way we would calculate tank volume, if you continued out the formula for sizing an expansion tank, it's going to take your expanded water, and you're going to divide it by your acceptance factor, and it's going to give you your total tank volume. So that 5.53 gallons that's expanding from my system at that pressure range that we'd specified earlier is going to give us 33%. So 5.53 divided by 0.33, it's going to give 16.8 gallons for our expansion tank sizing requirement. So as we know, we'd round up, so 16.8, round up to a 20, and our SX40V. Perfect, yep, that would work just fine for that scenario. But how can I get it, so now I'm going to manipulate something a little bit, and just to showcase my point of where a 32-gallon tank would actually have to be used. So what if I increase my fill pressure to 20? So I had 15, and I used a SX40V. What if I just, a lot of those, like a Calefi fill valve, you can just turn the knob and it'll increase your fill pressure. Maybe they wanted to get better pressure on the top floor. So you increase it just 5 PSI. Look what it does to that formula. So that same 5.53 gallons, the expansion didn't change. We didn't increase the system size. We just bumped the pressure a little bit. So 5.53 gallons, but now that I have a smaller pressure range, my acceptance factor went lower. It dumped. It got a lot smaller. Because now instead of a 15 PSI differential, I only have a 10 PSI differential. I only have between 20 and 30 instead of 15 and 30. So it's shrinking my available space for this tank to do its job, which is also going to lower the acceptance factor of it. It's not going to fill as much. So now in order to get enough space in that tank to make sure we're not increasing pressure too much and dripping the relief valve, I have to size up. So now I'm going to a 25.1 gallon tank, which if you round it up would be the SX60V, on the same exact system. All I did was I adjusted my fill pressure a little bit, and now I have a different tank size. So that's why all this stuff's so important. And you notice that max acceptance never came into play here. It was never a problem. I don't even need to worry about it. My tank sizing is based off of pressures and the volume of expanded water. It's very important. So as the pressure shrinks, we're going to need more volume, more air volume in the tank to make sure we're absorbing that, because of Boyle's law. They have to be proportional. In this case, it's inversely proportional. Less pressure range, more air volume. But if you run through the formulas, it'll always come out this way. It's just I'm trying to break it down to the point where I can kind of give a scenario for each reason why we change a variable, and then how that affects your tank sizing in the end. But in reality, if you went through tank sizing for every system, this would work its way out. You still see those final results, but this is why they're getting to that point on very, very similar system setups, but having to need two different tanks. So lastly, I want to jump into some common competitor comparison questions that we get. I'm going to give two examples here. So the first one I have is a Wessels tank. Wessels, they OEM for like Watts, and now they OEM for B&G. So there's a lot of Wessels tanks out there. They're just under different model names, but the vessels themselves are the same for the requirements and the specs and all that stuff. So I chose them as a common one just because of that, and then I chose our equivalent for the TTA80, which is our ST70VC. So you notice the tank volumes are very similar, but you'll notice that the max acceptance is very different. Admittedly, this is double ours. So at first, if you're looking on that with this, looking at that on a schedule, it might be a red flag or red light comes up of, ooh, well, can I cross that with ours? Our acceptance factor is very different. Very good question. So I'm going to give an example. This is just one way to look at it. There's multiple ways to look at comparisons between competitors. So this is just the one way I chose to do it for this example. If you want it to try to be compared a different way, or if you have a specific example, let us know. Either shoot us a question at the end of this, or you can ask us afterwards, because it may require us to get a little bit of information. It might not be quick enough for a Q&A, but you're certainly welcome to ask. We'll get back to you one way or another. But I'm going to give an example of a system that both the tanks work on just fine, and then I'm going to try to manipulate that same system to even try to come up with a scenario where our tank would no longer be applicable, but theirs were. Because a lot of times when we were trying to, this admittedly took a very long time to figure out how we can compare these, because all these different scenarios we had ended up with the tank needing to be sized up. So it's like, well, how can I get almost 23 gallons of volume in a 35-gallon tank? You have to have some really weird system setup that's completely unrealistic for most of them, which is almost the point I'm illustrating. It's most of that max acceptance space is wasted. It's never used, because no normal system, and I say normal, but no like average system is going to need that much volume in a tank that small, or that scale. So let me get into this example. So it's a thermal expansion tank, so it's going to be on a water heater, or a domestic water heater system. I chose a total volume of 500 gallons. So with 500 gallons, my static pressure on the system is going to be 100 psi. Again, a common relief valve is going to be 150 psi, so there's our pressure range. And then I'm going to have a min and max temp of 40 degrees cold coming in, and then it's going to heat up to 140 degrees. So for a system like that, your expanded water, if you ran through the math, it's going to calculate out to approximately 7.5 gallons, and your total tank volume is going to be approximately 24.72, call it 25. So on that tank, on that system, both tanks work just fine. Obviously, we're below max acceptance on both of them, and our total tank volume is within the range. You round up to these 35-gallon tanks anyway. But like I said, let's see if there's a scenario where I can increase if I can increase the expanded water to the point where my tank volume didn't go past 35, but I have that much expansion in there. So what I did was I decreased my static pressure to 70, so I opened up my pressure differential. And then the only way I can get that much expanded water is I had to bump my max temp up to 170, which, as we know, on domestic water system, I almost never seen 170 Fahrenheit. That would be one heck of a shower. I mean, yeah, you can use mixing valves and things like that. I'm sure it exists, but it's not very common, is the point I'm getting at. So if I had that pressure set up with a max temp of 170, I was finally able to break over that 11-gallon acceptance into 12.1. Because you needed a really large temperature differential. It's not very common. Okay, so if someone came to you, hey, I run my water heater at 170, so I love it really hot. I take lava showers. What do I need? Okay, yep, you got us beat in that case. I mean, all we'd have to do is size up to the SD80 VC, right? That's not a huge deal. But in that scenario, okay, yep, they beat us out. But it's not a very common scenario, and that's really the point I'm trying to get at. So if I know for scheduling and plumbing schedules and just sending out bids, they don't give you that information. I understand that. But if you were able to ask questions, or if you were out on the job site and you're sizing, or you're trying to replace and get some Wessels business, you can still do that. You just gotta make sure you understand what systems they're applying these tanks on. Because if it's the scenario right here, it's a very common domestic hot water system. You can use both our tanks. They're direct crosses. You can use either or. They're both going to function perfectly fine. If anything, we could argue that ours has higher quality and better standards, and it's going to last them longer. So that's how you make that sale in that scenario. And then if you had that weird funky one, okay, yep, maybe we have to move on to the next one. But I guarantee you're going to get maybe one of those a year. It's not going to be very common. And if I'm mistaken there and you're like, hey, I have systems all the time that look like this, let me know. I mean, I'm not out in the field. You see a lot more than I do. But I've never come across systems like this. If I have, it was once. So I know it's not as prominent as your typical domestic hot water systems. But for that scenario, hopefully you can see how similar those tanks are. Yes, the max acceptance is different, but you got to remember, it's all based on their system information. It's not the tank information. So if their system only needs 7.5 gallons, great. You can use both those tanks. It's not, oh, well, Wessels is better because they hold more water. No, they don't. They're going to hold 7.5 gallons. This is the only thing the system needs. It's kind of, you got to fight back and forth with that, of driving the focus on the system instead of the tanks. The tanks are victims of the system, if you will, or they perform only what the system is going to give them. They don't dictate their own values. Yeah, we can size them, but the volume going into them is given to them by the system. The tanks don't just magically create water. They're given water. So as long as we know how much water is going in, we can size these tanks confidently, and we can compete with these people no problem, because we know they're only going to use 7.5. So I don't care if the tank was full acceptance. It's irrelevant. It's all wasted space. So I'm going to give one last comparison. Just try to give a different angle from it. So we did a thermal expansion. I'm going to do a hydronic expansion with a smaller tank. So this is just a residential 4.5 gallon. So we're going to have an EX30 and an HGT30. So again, they're almost similar, or they're very similar, almost the same. But you'll notice that the HGT30 has a full acceptance tank. So they're both 4.8, tank volume and max acceptance. So I think they have bladders in theirs. Actually, I know they have bladders in theirs. But they're full acceptance. All right, so now we have that same question. Oh, well, that HGT30 holds more water. I was like, oh, I hate that statement. It doesn't hold more water. It just has a higher max acceptance. It's all wasted space. And I don't know any system where you're going to be able to get 4.8 gallons or even close to that in that tank, because it's going to be some obnoxious system, which I'll show you in a second. But my average control system here, I'm going to do 150,000 BTU boiler. If there's other variables like baseboards, but if it's just your typical baseboards, things like that, you're approximately 60 gallons of volume in that tank, in that hydronic system. 12 psi fill, 30 psi relief, again very standard. 40 degree fill, 180 degree max temp. That is like cookie cutter definition of a hydronic boiler system. That system is going to give me 1.7 gallons of expansion with the tank volume requirement of 4.1. If you look at both those tanks, cool. You can apply both of those, right? We're below max acceptance, they're below max acceptance, tank volumes match up. Perfect scenario to cross those over. But again, if we didn't know the system scenario, this would be hard to show that. I'm like, oh, if I'm just looking at two tanks on a shelf, if I don't know where they're going, yeah, I get that. But let me try to show you a scenario where we could use 4.8 gallons of max acceptance. So what I'm going to do is I'm going to modify my relief valve from 30 to 80, which I don't even know if that's impossible on most residential boiler systems. This is hypothetical. I'm trying to give an example. So if we increase that relief valve to 80, and then we took our max temp and we increased it all the way to 250. In reality, we can't do that because both these tanks are rated for 240, so we're already exceeding that. But that was the only way I can make these numbers work, is I had to have a huge pressure range and a huge temperature range to try to work it out where you can use a tank that was less than 5 gallons with more than 2.5 gallons of expanded water. And I made it happen. You know, I did. So now I have 3.4 gallons and the tank is 4.7. So we had already had to size up our actual anyway. You know, okay, just use an EX60 or an EX90. Problem solved. But that is, I guess, one scenario where conceivably you would have to choose the HTC30 over the EX30. Now I really would challenge you to find a system that has that. That almost never happens. So it's, all right, well, if I have my average system, there's no reason why I have to say, oh, well, HTC30 holds more water. No, it doesn't. It only holds 1.7 gallons. It only holds what the system gives it. So if I know my system's going to give my tank 1.7 gallons, I can apply both those tanks. And again, then you can compete with the quality and the lead times and pricing, all that stuff. You've already tackled the fact that their tank isn't going to do any more work than ours is. It's all dictated by the system. So hopefully that helped a little bit visualize some of the stuff we talked about. I know those are tough concepts. You know, even working through it, I'm trying to find different ways to explain it, but hopefully we got you to a good spot. So as always, we're gonna go into our 5-minute break. We want you to ask us questions. You know, anything else you want to see, or if I can try to reiterate some things, please let me know. We'll take a look at those questions and we'll dive into the Q&A and we'll get those questions answered. So thank you, and we'll be right back. All right, everybody, welcome back. Thank you for those of you that sent in questions. Really appreciate it. We're going to jump right in just for the sake of time. I know this is a longer one today. So, Gabe, can you read off that first question?
All right, so our first question is from an Inner Circle member. Can you utilize supplemental drawdown in a VFD application?
Okay, yeah, so for supplemental drawdown on VFDs, absolutely. I'm surprised I didn't mention it. So VFDs are a very common instance where we'd use supplemental drawdown because you're not using a nice wide pressure range like you would on a traditional well setup. So I've spoken at customer conferences with pump manufacturers that build pre-built skids, so they have their pumps with a pressure vessel and they ship that out to a customer, and they'll use our vessels on there. And that's exactly what they're doing, is sizing for supplemental drawdown. So they'll have a desired downtime that they want on their system, whether it's 30 seconds, 3 minutes, a half hour, I don't know. They always have kind of something they're aiming for to have downtime for their equipment, because that obviously helps their longevity. So they'll size a tank according to their expected flows and demands on the system to make sure we're meeting that specification. So it's used for that peak demand stuff. So if we're sizing a booster system for a municipality, we know that our peak demands are, 6:30 in the morning and 5 o'clock at night because people are showering and cooking dinner and whatnot. So we'll be able to estimate what that flow demand is, see where it fits on that pumps curve. If it's okay, nope, we're still in the efficiency, we're in that spot, or hey, we're going to need some help. We'll be able to size the tank to make sure we bridge that gap, and their customers are going to get steady flow and good pressure the whole time. That's one way to do it. Another way is for basically those small midnight demands almost. So if it's 3 a.m. and somebody opens up the faucet for a glass of water, we don't want their 18 horsepower booster pump to turn on. So what they do is we'll use that tank's volume as well to make sure that we're supplementing that little differential just to help fill some of those really small demands in the middle of the night. That way you're not firing on and off those motors all the time. So that's a very, very common application. It's a good question.
All right, our next question. Can you use extra drawdown to solve low pressure issues?
Low pressure issues. So I'm going to dig in that question a little bit. So flow and pressure are different. And if you watch the RP presentation Gabriel did, that we went through that a little bit. So when we're sizing for supplemental drawdown or using the extra drawdown in the tank, or just any pressure tank in general, it's supplying volume, not pressure. And I know it's called a pressure tank, but in reality, it's giving you volume. So when we size these tanks for these systems, the idea is that we're trying to fill a gap in the volume, or we're trying to solve a volume requirement, not as much of a pressure requirement. The reason that gets misconstrued a little bit is because when you run out of volume, you also run out of pressure. And that's the symptom that the customer sees more so of, oh, I don't have any more water pressure. But the reason you ran out of pressure is because you ran out of water. So it's a consequence of running out of volume. So we're solving the volume problem. We're introducing a pressure vessel with a certain amount of drawdown to supply volume to the system, and therefore will also fix the fact that they run out of pressure because of it. So I guess it's indirectly solving the problem, but in reality, we're not actually tackling the pressure situation. We're tackling a volume situation.
All right, that was another good question. This is our last question for today. With crossovers, what's the difference between full acceptance and partial acceptance bladders?
Yep, that's another good question. I took a peek beforehand, so I had something pulled up on my tablet here. Full acceptance and partial acceptance bladders are both replaceable bladder tanks. They just have a little bit of a different setup. So just looking at this image here, on the left you see the full acceptance, the right-hand side you see the partial acceptance. It's ultimately their design. So full acceptance is, as we've talked about in the past, in theory, there's no constraints on it other than that top flange. So that bladder can fill and drain, and it kind of has free range throughout the inside of the tank, which has its benefits, but also has its drawbacks. So what the partial acceptance tank does, and I know it's not shown in this, but there's actually a diffuser tube that runs right up the center of that bladder and fixes it at the top. So that bladder will cycle horizontally like this instead of vertically up and down, and that's why it makes that Christmas tree looking shape. For those that are curious. So because of it having a fixed diffuser in the center, it makes sure that that bladder is not going to fold and rub and kind of twist on itself like a full acceptance bladder potentially could. So it kind of gives you a little bit of a peace of mind if you don't need a large amount of drawdown within the tank. So it's kind of that bridge between a diaphragm tank. So it's a little bit bigger than a diaphragm tank, but you don't have to go all the way to a full acceptance bladder. It kind of meets you in the middle and gives you a little bit of the benefits of both. The replaceability of a bladder, but also the more fixed design like a diaphragm is to give you the partial acceptance bladder. So you'll see that on specs every once in a while. They'll call out one or the other. That's what they're asking for. So that's a good question. And Gabe did say that was the last one, so I'll wrap up here. If there's any more questions y'all have, feel free to send them in. Give us a call, shoot us an email, visit our website. We're happy to help you out if there's a certain sizing situation where you're trying to utilize some of this stuff and you just want to run it past us. That's what we're here for. So without further ado, we're going to wrap it up. Enjoy the rest of your day. Thank you very much for watching.